All right, let's talk about this method of initial rates.
Yeah, I love her.
I need to go back.
Oh, I officially ran out of paper in this
Yeah.
notebook.
Well, I'm 2 subjects in, 2 3 subjects in. So.
I'm sorry to cut you off.
I guess I need to work harder. I feel like I should.
No.
I feel like I could feel two.
What? What? Well, this is like chem, history, and also calculus, because my calculus one, my 5 subject calculus one ran out of paper.
Ah.
So.
Yeah, see, that should be work 2 or 3. All right, so that problem set I gave you today, okay, that is the method of initial rates. We actually did some of that on Friday. What we did on Friday was basically just an intro, participation. It kind of would have been along the same lines if we'd done the geometry lab. It's not really a lab, so anyway. Kind of like that worked out. On this method of initial rates, I need to go back on the quiz. And there's a full problem like the 2 problems on your problem set. Okay, there's actually 2 on there and I need to go change it. But what we're going to work through today, or at least get started with, that method of initial rates. Okay, you're going to see the same thing on this kinetics quiz. This kinetics is probably my favorite chapter. Just a lot. It makes a lot of sense to me. When I got to grad school, like undergrad, I had some really good instructors. I had a couple of not so good instructors, but grad school, basically, I had a whole lot of not good ones. But the best one I had, he was a kinetics guy. Maybe that's it. All right, so let's kind of reinforce what we did on Friday. To do that, we kind of have to understand what we're after. So we're trying to figure out the rate of the reaction and everything that goes with the rate. All right, so concentration goes with the rate. Time goes with the rate. We can influence different things that would change that rate. Okay, we're going to look at something like catalysis, using catalysts to help facilitate the reactions. At its very basic premise, to get a reaction to happen, we're going to have collisions between molecules. Okay, and that's something we're really going to harp on in the kinetics section. Okay, we have to have those collisions. Sometimes those collisions are with the same compound, not the same molecule, the same compound. Sometimes those are different, right? And we're going to kind of differentiate a little bit. Some of that's a little hand wavy, like, look, it's going to happen with itself, and poof, we got a product. A little bit of hand wavy going on. That's right. All right, so we need to know what's going on in terms of solid, liquid, gas. Obviously, gases are going to move faster, but there's no more space. What concentration that we start with? What concentration we have at time, whatever. Okay, so the more of those molecules that are hanging around, the more potential for collisions, the more potential to move from reactant to product. Temperature is going to play a role. Okay, we're not, so early on, we're not really going to harp on temperature. At the end, we will, as we kind of traverse through the method of initial rates and then integrated rate law. Calculus people didn't like have a seizure. I'm surprised. we're not gonna worry so much about temp, but then we're gonna change it and see what happens to our reaction. Okay, so higher temp, faster movement, more collisions. Also, if we add something that facilitates the reaction, okay, that is called a catalyst. That catalyst remains unchanged from beginning to end. A lot of times, a catalyst is a surface. So like platinum is a catalyst because it provides a surface for those reactions to happen. What it really does is orient those molecules in such a way that when they hit each other, they change from reaction to product.
So if you were to find it, it would be a surface that,
Facilitates. Okay, this is probably, me and my buddy did these notes, and these are actually, I hate to say my best notes, but they're probably my best notes. There's some scribble on here later, we just, we wrote on there using the old school way that we had. This is probably the best line. It doesn't tell you what a catalyst is, but it tells you what it does. And they're going to increase the number of productive collisions. Okay, that surface is going to orient those molecules such that we get productive collisions. Okay, meaning we go from reactant to product. All right, so let's define rates, forward and reverse. Okay, rates are going to be change in concentration with change in time. Calculus, folks, what's this sound like?
concentration over time. I know
You're
this,
changing something over a change in time, like,
distance equals
the
rate
change
over
in
time.
y or the change in x.
No, don't.
Yeah.
is it starting to look like that?
Stop.
Oh,
The derivative.
that's a derivative!
No, it's the thing that I was stressing about Friday.
I finally got rid of calculus. And now it's back.
Are we doing derivatives, Mr. Rowland?
Only roundabout.
So,
You're not gonna take the derivative of something.
Of a function. No derivative of
Actually,
functions. Thank
I would
God.
rather take the derivative of something than be like, what am I doing? Because I know how to take the derivative.
I mean, the rate, the reaction rate by definition is a derivative.
Rate equals.
So
Yeah.
I'm taking derivatives of trait functions.
Ooh,
You don't have to worry about that.
what?
What's a derivative?
I don't know.
It's the thing you had before
It's
you got to the
something.
thing you were, so you're basically solving equations backwards.
Yeah.
And it
That
sounds
sucks.
Stupid.
So anytime we change a variable over a time frame, okay, that is a rate, and that is by definition a derivative. Okay, we're not gonna like take derivatives of functions. We're just, you actually took the derivative by finding the slope of the tangent line. Right?
Yeah.
We know.
Teaching and doing some calculus. All right, so average rate is over a specific time interval. If you look between time 0 and time 20, that's 20 seconds, minutes, hours, whatever. And then the instantaneous rate is what you were looking at on Friday, so at that point, at that particular time. So those are two different definitions.
Instantaneous is at one particular time.
Correct. All right, so here's what you did on Friday. I told you we had some scribbling. And he writes better than I do, so. Okay, so you were so notice some of you made a super steep line at time 0. Right, so some of you had a line that looked kind of like that. And so we went back and kind of mapped the curve. And this is not the data that I gave you, it's different data, but it serves the same purpose. So when we were looking at this, we're like, all right, here's the curve is going to curve upward there. So that is our best guess on a tangent line. And then we took the slope of it. And we just so we circled the points that we used right there. We were just estimating like you guys were on Friday. And then we looked at this time frame. Okay, drew another tangent line, and then took the slope of it. And you could do that as many times as you needed to do. But the whole point of doing this, we actually calculated the average rate between those time frames. And the point was, so he can't stand it when his units aren't right. Sometimes still don't know.
Slow down with that.
So notice that the rate is going to slow down as we use up some of our reactants, which makes sense, right? Because at first you have all the reactant, and then as time goes on, you're going to have less reactant, no problem. And as we disappear, that rate will be negative. If we're talking about appearance for products, that rate is going to be positive. If we look at the ratio of the rates, okay, they are related to the coefficients in the balanced chemical equation. Okay, if we're talking about A and B, they're going to disappear, so there's a negative in front. If we're talking about C and D, they're going to appear, so it's positive. If you wanted to compare, so if you knew the rate of A, then you could find the rate of C. Right, because all of these are equivalent. The rate equals this and that. They don't have any problems on your problem set, but I'm pretty sure in your little quiz study guide there's one like that. And when we go through an example, maybe you can follow it, maybe you can't. Okay, we just plug in the numbers to find the rate for the other guy. Okay, if it's disappearance, it's negative.
What is this?
What's what?
I can't even
Exactly.
make it.
What's what?
It's by the 2/3, and it's like over
All right, so here's the reaction. This is what we pulled off of, like that previous slide, where this is the rate, right? And so that means we're going to use those coefficients. That's it there.
Oh, okay.
All right, so we know this rate.
Oh.
We're going to find that rate. Okay, that whole, we know this rate, and we're trying to find this rate. So if you just wanted to say rate, that would be fine too.
Actually scared me.
All right, so let's dive into the method of initial rates. And we've already looked at the rate law. So rate is going to equal a rate constant K times the concentration of A raised to some power. And Normally that's going to be a whole number. And then times the concentration of B raised to another power. One thing I really do want to emphasize, so M and N, and we're going to call them M and N. They're not A and B. They're not small a, small b. They're not the coefficients. Okay? No and no. Resist the urge. Sometimes it works out that way. Happy coincidence. So resist that urge. It's a very common lazy mistake, I guess.
So
Easiest way to say it.
M and N could be the same, but oftentimes they're not. So,
Right.
Okay.
That's A and B. And M and N are normally going to be whole numbers, like 0, 1, 2. Normally. There are some instances where we have fractions, normally halves. Overall reaction order, okay, overall is going to be M plus N. Okay, that is easy money points right there, like double easy money points. Goodness gracious, please don't miss that. Out of all the things we do in here, like I'll see 30% of my kids, they obviously they don't understand it because normally it's like 0 plus 2 or 1 plus 1. Okay, so don't. That's easy money points. Okay, the exponents always have to be from experiment. Okay, so I have to give you some data. That way you can find them. Or I have to tell you what it is. One or two. I want to come back to this. All right, so here's kind of the process for determining or using the method of initial rates. Okay, so we need to find some trials where the initial concentration is constant. And then you're actually going to be able to see this. If we do a couple of them, you'll actually be able to look at it and go, oh yeah, all right, this one's first order. Or, oh yeah, this one's second order. But we have to walk through the process. Okay, so we're going to find which trials are constant. We're going to look at the rates versus the concentration changes. All right, so what we're going to do initially is to get rid of one of the reactants. So if they're the same concentration, we're going to get rid of those. Then we're going to see how the ratio of the rates compares with the ratio of the concentrations, which is the last thing we did on Friday. All right, so on Friday I said, hey, you know, the ratio of your rates was like 1/4, and then the ratio of the concentrations was 1/2. And you told me that X was 2. That's what you guys. Maybe it was steep, so X would have been close to 1. Okay, that's exactly what we're doing with the rate stuff.
That is a derivative.
What?
Rate is a derivative.
Yes.
When you write it like that, I can see
Can you
why.
see it? You see it
Yeah,
now?
because it's scary.
All right, so that is what we're going to use. And again, like you're going to see it after we do a couple. You're not going to have to write everything down. You're going to see it. Okay, but we do have to walk through the first time or two.
Is that A and then M and L1? M and 1?
So the first concentration that you use, or the first experiment and the second experiment. And we can divide them in different ways, right?
For certain, I was scared that that was an integral. 'Cause there
Oh,
was a
not
top
yet.
and
It's
bottom.
coming.
Okay.
It's coming.
Integrals are coming. Oh gosh.
They are definitely
I'm not ready for that day.
All right, so if I look at this data, okay, if I look at experiment 1 and experiment 2, all right, so notice in experiment 1 and experiment 2, concentration of A stays the same. Okay, we're going to double the concentration of B, and the rate is going to stay the same. So without like crunching the numbers, can you tell me the exponent for B?
Wait, you're saying that from A to B, experiment 1 stays the same. So,
So A stays the same, that means we can get rid of it. I'll show you
Oh.
mathematically in a second.
yeah.
Hey, we double the concentration of B, but our rate doesn't change.
Okay.
All right, let's write it out.
Oh, I'm sorry.
All right, I'm gonna put experiment 2 over experiment 1. Because, okay, this is double this, that way I can deal with whole numbers and not fractions. If you like fractions, deal with fractions. Okay. Do all of that. Okay, so I'm gonna write down the rate. The concentration of A, 1. Concentration of B. Alright, so I've done number 2 over number 1. Right. Alright, because those are the same concentrations, that is equal to 1, and it doesn't matter what M is right there, because anything if that's 1, then we've taken care of it. Alright, so what's this divided by this? 1, right? Okay, we can kind of forget to show this sometimes. All right, these two are equivalent, right? Because they're the same exponent. So what's 0.2 divided by 0.1?
2. Or 0.2. No, it's 2. Sorry.
1 equals 2. So does N equal 1?
No, it's the square root.
Wait, 0. Because anything to the 0 is 1. So N
Or the
equals
1/2.
0.
What's that?
Is it the 1/2 or is it 0?
The 1/2 is the square root.
N, yeah, 1/2 is the square root. So N is 1. Or is it 0? Or is it 1/2?
No, everything.
But see, just looking at that, going from point 1 to point 2, I couldn't have told you it was 0.
No.
So anything raised to the 0 power is 1.
Right.
Yeah.
And since the rates didn't change,
Mhm.
we know that this side is 1. Right?
Okay.
And so it doesn't matter what this is.
So that's what you were trying to get us to see.
Yeah, that's what I was trying to get you to see.
Yeah.
It really was.
Hey, I see it now.
All right, so let's look at, well, hold on. So we took care of N, so now we need to do M. Okay, so I'm going to use 1 and 3 because those are the two where B is the same. So we know that this is going to go away. All right, so let's try again. Right, so by what factor does the rate increase?
4.
4, right? By what factor does the concentration increase? 2. Right, 0.1 and 0.2 is a factor. We're looking at factors because these are exponentials, right? Okay, so 4 is here, equals 2 to the M.
2.
So M is 2.
I see it now.
Right.
So overall order is 2.
The M plus N?
Yeah.
Oh my gosh. I think I'm
Second order is the highest order that we really consider, and anything past 2, we looked at 3 in grad school, and it's just, the math is ugly. And it really, the orientation has to be so stinking weird for it to have that third order type of kinetics, that it's just, it's not a great explanation. And it doesn't happen probably, but the chances are super, super, super small that it happens. And I think, yeah, we worked those out. So. We didn't go full bore.
breathing into a paper bag.
On that one. But there's a couple to look at.
You should see a doctor because you could have done
All right, so take a crack at figuring out M and N.
on A.
Your problemo set there.
Do you have a paper bag?
Yeah.
Okay.
Sorry.
You're good. That was kind of random.
Here's a,
Have a plastic bag.
That might work.
He's got a snack bag.
That's right.
Apparently breathing into a paper bag helps with hiccups. And I tried drinking water and it didn't work. And I tried holding my breath and it didn't work.
Hold your breath longer.
sit down now.
Like Superman.
I just need my diaphragm to calm down.
You just need to get back in line. That's what you need.
Okay. What? I don't know. What? Is hiccups grounds for?
Now, your diaphragm is not in line with. It's not in line with your muscles.
Oh,
that
so
tends
that's
to
why
breathe.
breathing into a paper bag helps. Because it helps you get that breathing. So I'll just breathe normally. I sound like I'm really mad.
When I was reading real fast, and something happened right here. It was like a big bruise.
No, it
But
didn't because I
lastly,
hate
like,
it.
I didn't stumble. I don't know, my legs came up from underneath the bag. Pushed me. You sound like you're an asthmatic about to have an asthma
I keep
attack.
getting hiccups, girl. It keeps coming back.
Drink a lot of water.
Oh, if you drink water and then you like look down and you swallow.
Water. I'll do that later. Maybe.
I hate when do you ever get those days where you have like hiccups nonstop?
Yeah.
Like you
just
never
wanna,
get
like,
hiccups,
stick a fork
and then
into it.
one day you get hiccups nonstop. Always have some cold water.
It's a little drastic. What you doing?
Trying to cool my coffee off. I don't have the iron mouth my grandmother had.
Want me to hick on it?
Hiccup.
Hick on it. That's what I meant.
You should
Maybe
get one
it'll
this,
help my diaphragm or something.
Hughes has.
Okay.
It's like a little disc, and I just put it in.
What's the
You
point?
put your coffee pot on. Just drink your coffee.
Yeah.
Oh, 'cause normally what I do.
My chem teacher had one
Normally I like hold my breath and then I drink water
Oh,
while
what's all
of
that?
those.
and it normally works.
Food too
And that's
long.
the only thing that's ever worked for me.
Mr.
Right now it's failing.
This
There you
okay. So this is the -3, right?
Mhm.
This is -4. So that would be 0.13 instead of 1.3.
Swallow the water, that's how you do.
No, I just I hold my breath normally and do it, and then like I make sure I do like a really hard
Okay,
swallow. So
okay, so
like,
13 divided by 3.2. What is that?
and
So
then
yeah, that's still a long
because it just like
blank
makes it
number.
4.
Go
Just
back.
use 4.
Okay, that's thank you. Okay, so he said, so whenever you divide those two, like you do, it gives you, you have to turn that 1.3 into 13 to make that to the -4. And that gives you that number, and he said just use 4. So then we have here equals 4, so then m equals 2. And then, you know, m equals 2, so m plus m equals 3.
B is within, B is in. Does it matter which experiment you put on top?
No, mathematically it's going to come out the same, but I like to put, so if I was doing experiment 1 and 2 to
Right.
get rid of A,
Right.
I would put 2 on top.
Okay. Oh, because 3.2 is larger than.
Like I told them I didn't want a TV. Like I really don't want it. I use my own smartboard because I could like put things right here and I could work things. Like I could work this on the board, like right in that spot where it goes. So I told them I didn't want a TV. And they're like, too bad, you get a TV.
That's what how Miss Hunter says. She still has her old like box TV. She still plays stuff on there. She
Bless
remember
you.
those old speakers that were on the wall?
Oh yeah.
What happened to those?
They disappeared. Like
I remember Miss Hoffs, and they would always have to like stand on a chair, and like, click on the button, and then they just suck. It was like,
they were not good at all. Yeah, they disappeared like
I
everything
thought it was
else.
the other day.
Like the smartboard. You know? Like I just came in one day during the summer, it was gone.
I just like how it's like a 60-inch.
What do you need, Kate?
It takes up your whiteboard. It's
Right,
this far.
yeah, it eats up my whiteboard. I can't work things on it. I guess I could wipe it off.
Would you rather have the bigger initial rate on top or the bigger concentration of whichever one you're trying to solve for?
They should be one and the same,
Okay.
right? So like, if you're looking at these two, right, this is bigger,
Yeah.
okay, so that matches that. If you're looking at, because this is to the -3.
Okay.
The other two are to the -4.
Mr. Owen, I'm not sure I'm doing this right.
On this?
I did 3.